Now that we have discussed the very basics of ventilation, airflow, and airborne contaminants, we can discuss how to implement methods that can help control those hazards. There are a few different categories of methods for controlling airborne hazards, particularly in the workplace. These include dilution, exhaust, fans, and respiratory protection. Air cleaning is another kind of more complex category that's a bit beyond the scope of these lectures, but there is an optional reading for this week's material about air cleaning if you would like to know more specifically about those kinds of technologies. First, we're going to discuss dilution ventilation. So dilution ventilation is a method that adds clean air to polluted air in the room, or it exhausts or removes polluted air from the room. This is the simplest and most common form of ventilation control, and it can be achieved by either natural or passive methods or mechanical methods, or a combination of the two. You can see an example of passive dilution in this slide, a passive dilution ventilation in this slide, where we have a room that is ventilated with the use of open windows. So you can see the windows are open on the sides, and the air represented by those arrows, cooler air, is flowing into the room, cool, clean air. And then they're also utilizing a temperature difference. So the cooler air is flowing into the windows, and the room inside is warmer. So then that air warms up, rises up, so the contaminated air gets pushed up and out of the openings in the roof. So this is a passive way of using dilution ventilation to clear dirty air out of the room. Mechanical dilution ventilation usually involves something like a large exhaust fan that is placed in the walls or the roof of a building, which we will discuss in just a moment. There are some limitations to dilution ventilation. So dilution ventilation is great, like I said, because it is simple, it is often very cheap, and it's pretty easy to do. However, when used to control chemical pollutants, dilution must be limited to situations where the amounts of pollutants generated are not very high, their toxicity is relatively moderate, workers don't carry out their tasks in the immediate vicinity of the source of contamination, and the emission rate of contaminants is relatively uniform. And this is because, like I said, there are some limitations to dilution ventilation. So these limitations are that this kind of ventilation does not completely remove contaminants. It can't be used for highly toxic chemicals because it is just not effective enough to remove these highly toxic chemicals to a point that is safe for someone to breathe in. It's not effective for dusts or metal fumes or large amounts of gases or vapors. It also requires large amounts of exchanged air to be heated or cooled. So like in the last slide, in that example, you've got cool air coming in the windows. Well, obviously that means that all of that air that comes into that room, if you need it to be a comfortable temperature, you're going to have to heat up a lot of air, which could have an effect on your utility bills and things like that. And then also, dilution ventilation is just not effective for handling surges of gases or vapors either. So this is something that is a lot better for contamination of the air that is relatively consistent. The general principles of dilution ventilation rely on static pressure differences in the air moving in and out of the room, temperature, location of inlets and outlets, so that's location of where the air comes in and location of where it goes out, and then recirculation of exhausted air. So remember that air flows from high pressure to low pressure, and this creates a static pressure difference. We're able to use this to our advantage when we're designing dilution ventilation controls like those seen in the example on this slide. So the first example on the left utilizes a passive air inlet and an exhaust fan at the outlet. So on the left side of the room, in the blue, you can see it's representing air passively coming in. This inlet could be a window or a vent. And then on the right side, you can see the pink arrows represent air going out through an exhaust fan at the outlet. So the exhaust fan at the outlet is extracting the contaminated air out of the room. The extraction creates an area of negative pressure, which causes the fresher replacement air to flow through those doors, windows, or low-level intake grills. The second example, the one in the middle, utilizes a mechanical supply of air in a passive exhaust system. So this is kind of the opposite of what we just discussed. So this way we're mechanically pushing clean air into the room and allowing the dirty air to passively exit through the exhaust system. So this results, the fan pushing the clean air in results in a lowering of the neutral pressure level, or the level in the building where the interior and exterior pressure levels are equal. This lower neutral pressure level then drives the air out the passive outlet. And the third example on the right, this utilizes fans at both the inlet and the outlet of the room, which creates a balanced pressure system. So you're using a mechanical force to push the air in and to draw it out, and so you have a balanced pressure system. Local exhaust ventilation, this is different from dilution ventilation, is used to control air contaminants by trapping them at or near the source, as opposed to pushing the contaminants through the room like with dilution ventilation. So if you are doing something that requires working with contaminants in one space, you can use local exhaust ventilation to capture those contaminants at the source. This is generally a far more effective way of controlling highly toxic contaminants before they reach the workers' breathing zones. So if you remember from our previous lectures, one of the common themes of how we control these hazards is that it's usually best to control the hazard at the source if possible. So we've got source, we've got path, and we've got receiver. So in this case, the source is, whatever the action is that's creating these airborne contaminants. So it's best in most cases to try and control that hazard at that source. And this is what local exhaust ventilation helps to do. Local exhaust ventilation is often the preferred method if air contaminants pose a serious health risk, if large amounts of dust or fumes are generated, if increased heating costs from ventilation in cold weather are a concern, if emission sources are few in number. So like I said, if you're just working, say you're in a lab and it's just you and you're working with xylene and it's putting off all of these fumes, well, you don't need to change out the air in the entire room if it's just you working in this one little area at the bench. You just need to make sure that you have proper ventilation in that area where you are. So you would use some sort of local exhaust ventilation in that case. And it's also good to use local exhaust ventilation if the emission sources are near the workers' breathing zones. Local exhaust systems tend to have 5 basic elements. This is a picture that was on a slide a few slides ago, but this is a really good example of the different elements of a local exhaust ventilation setup. So you're going to have the hood, which captures the contaminant at the source. You have ducts, which transport the contaminants through the system. You often have an air cleaning device. You have fans, which move the air through the system and then discharge the exhaust air outdoors. And then you have the exhaust stack, which is where the air kind of goes through and exits out into a safe area. So I'm going to talk about some of these elements in more detail now. Exhaust hoods are very important parts of local exhaust ventilation systems. They serve as the point of entry of air into the system. And the general goals for exhaust hoods are to adequately control air contaminants, to not interfere with the operation being ventilated. So obviously, if you're doing something that is generating contaminants and you need to get rid of the air contaminants, you don't, whatever exhaust system you have, you don't want it to be in your way or making it harder for you to do your work. Another goal is to use minimal airflow to do the job and impose minimal resistance on a fan. There are multiple kinds of hood types, and each of these hood types is good for different purposes or for systems. So if you're designing a local exhaust ventilation system, you need to think about what it is, what you are trying to control, and what the best hood would be for that purpose. So the three main types of hoods are enclosing hoods, in which the contaminated air source is already inside the hood; receiving hoods, which use a natural motion of contaminated air into the hood; and then capture hoods, in which contaminated air is, the source of contaminated air is outside the hood, and the natural motion is not into the hood, unlike with receiving hoods. Enclosing hoods, or as they're sometimes called, fume hoods, surround the process or point where the contaminants are generated. These hoods are preferred wherever possible because they capture the most amount of contaminants. Some examples of enclosing hoods are laboratory fume hoods, biological safety cabinets, and glove boxes. So if you've ever done research in a basic science lab, you've probably seen these sorts of things. On the right is a laboratory fume hood. So if you are working with some sort of chemical that is giving off dangerous fumes, you are instructed to work with it inside this laboratory fume hood, like this lady is. So you've got this glass partition that can raise up and down, you can raise it up just enough so that you can put your hands inside the hood and do all of your work inside the hood. And this actually uses a mechanical process to pull the air out and away and into a safer area, so that the people in the lab are not exposed to these air contaminants. And on the left is a biological safety cabinet. And this is something that if you're doing cell culture work or something along those lines, is used not only to protect the workers, but also to keep that area sterile and clean. Receiving hoods are designed to receive or catch the emissions from a source that has some initial velocity or movement. So in other words, if you are doing something that is creating fumes that are gases that are moving, receiving hoods help to capture that movement and pull that contaminated air into the hood and into the ventilation system. Some examples of receiving hoods are canopy hoods that receive hot rising air and gases. Capture hoods are hoods that are located next to an emission source without actually surrounding or enclosing it. These kinds of hoods are good for if you're welding and creating the fumes, but you can't be welding in an enclosed space, or if you're doing something that requires grinding a material that creates a lot of dust. You can do that. On the right here, there's a picture of a downdraft hood for hand grinding. So you can grind something over this and the dust from it is pulled down into the hood and then through the system. An example of this that you might see in more everyday life is, for example, if you go to a nail salon, a lot of the nail processes require a lot of generation of dust, and so they often will use special, they're like almost little fans, they seem like little fans, but they're really these kinds of capture hoods that pull this dust generated from the nail designs into them and away from the people so that they're not exposed. These kinds of hoods can have round or rectangular openings or slot openings, and all of these openings can be either flanged or unflanged. Now that we've discussed kind of the two main types of ventilation that we can use, so dilution ventilation or local exhaust ventilation, it's important to understand how to know which kind of ventilation to use. How do you know when to use local exhaust ventilation versus dilution ventilation? This depends on a few factors. So first and foremost, the air contaminant qualities are very important to consider. So what the air contaminant is, how much is it in the air, that sort of thing. We also need to consider source characteristics. Where are the contaminants coming from? Is it a localized area or is it spread throughout the room? Do you have one person creating these air contaminants in a very small part of the room, or is this a large manufacturing process where you have a full room of people who are all generating dusts or gases or those sorts of things? Is the source easily localized? Like I said, if there's somebody working with a chemical at a lab, are you able to easily localize that source to just one spot or not? You also need to consider air treatment. So are you using other methods of air cleaning in addition to the ventilation? And you need to consider energy conservation. Is it going to cost too much to use local exhaust ventilation when using dilution ventilation can be done in a satisfactory manner? Or like we mentioned with dilution ventilation, you have to take into consideration the cost of, or the energy cost of heating an entire room if you're introducing cold, clean air into that room. So these are questions that you need to ask yourself if you're trying to figure out what kind of ventilation to use. When you're not able to sufficiently control the ventilation through local exhaust, dilution, the use of fans, or the use of air cleaning, you can use respiratory protection. So we discussed, you've got your source, you've got path, and you've got your receiver. So we've just discussed methods to control air contaminants along the source and the path. Now this would be a way to help control these hazards at the receiver level. Respiratory protection devices are PPE, personal protection equipment, worn by a person to protect against the hazards caused by atmospheric conditions around the person. These can include everything from simple disposable masks, such as the masks we all became accustomed to wearing starting in 2020, all the way up to kind of high-tech spacesuit type respirators that you'll see somebody wearing in a really hazardous condition. This picture here shows the anatomy of a respirator. Some important factors of a respirator is that a face seal is tightly around the face to keep contaminants out. There are straps that hold the mask snugly in place. There's often a filter or pre-filter that can trap particles. And then the rest of it kind of depends on the design of the respirator that you're using. There are two basic respirator types. The first is air purifying respirators, and these are respirators that remove or filter hazardous components from ambient air without providing clean air or oxygen. So these are kind of, I think, the respirators that we are all tend to be very familiar with. N95 masks and the respirators that are like in the picture I just showed you. So these are things that don't supply you with clean oxygen or new oxygen, but instead they filter or remove the hazardous components from the air. And then the other category of respirators are air supplying respirators. These are respirators that have a self-contained air supply or a fixed air supply with a hose. So they do the job of the air purifying respirators, but then they also provide you with clean oxygen. Air purifying respirators definitely have some advantages. They tend to be very simple and low cost, and they are highly effective if properly used. We will discuss about the proper use. We'll discuss the proper use in just a minute. This is kind of a big thing with respirators, is making sure that they're actually properly used, as with really any receiver control. It depends on human behavior. But the limitations of air purifying respirators can often be the occurrence of leakage around the face piece, penetration through the filter, and insufficient protection in ultra hazardous environments. So these kinds of air purifying respirators are good for situations that are not incredibly hazardous or incredibly dangerous. There are several face piece styles for air purifying respirators, such as a mouthpiece, quarter mask, half mask, full face, hood, or helmet. And there's also negative pressure air purifying respirators, which are lung powered, and then there are positive pressure air purifying respirators, which are mechanical. You can see some examples of these styles of air purifying respirators here. So we've got one that is a full helmet, and then we have one that is a half mask and one that is a full face that doesn't cover your whole head, but it covers your eyes as well as your nose and your mouth. Air supplying respirators have advantages as well. Obviously, the biggest one is that they are the most protective form of respirators, and then they also don't cause any oxygen deficiency. So you never have to worry about not getting enough air through your ventilators or your respirators because they have their own supply of oxygen. However, there are also limitations for air supplying respirators. One is the potential for contaminated air, so the air that is being pumped in is possibly contaminated, which would be an issue, of course. Potential for loss of air supply. Your air supply is never going to be unlimited. Leakage around the face piece, restrictions on movement or time in the atmosphere, as well as cost and complexity. These are, of course, going to be much more expensive than the other kinds of respirators because they require a lot more parts and they require the introduction of oxygen. Most common air supplying respirator face piece styles are half mask, full face, hood or helmet, and full body. So these are some of these things that are pictured here. And like I said, they can either have a self-contained air supply or they can be hooked up to a hose that is hooked up to another air supply. So we've got this guy on the left in the blue. He's got this entire full body respirator system going on, whereas the other guy has the full face style respirator, and he is hooked up to a hose that would be connected to an air supply. As with any hazard control at the receiver end, it is imperative to ensure that the receiver or the person being exposed to the hazard is aware of the best options to use for protection and how to properly use the protection. So it takes a lot of training to make sure that somebody is using the respirator properly. Otherwise, it's not going to be doing its job. So for respirators, it is especially important to choose the proper type of respirator and make sure that it fits properly. So to choose the best kind of respirator, you need to take several things into consideration. The primary consideration is really just what hazard you are trying to control. So is it, what is the physical and chemical state of the contaminants? How much is it in, what is the concentration of the hazard in the air? How long are you going to be exposed to the hazard? What are the exposure limits? And what are the toxic effects of the contaminants? It's also important to follow NIOSH guidelines if you're using respirators in an occupational setting. So you need to make sure that you're only using NIOSH approved devices in these sorts of settings. Fit testing is extremely important for respirators to ensure that they're proper use and protection. There are multiple factors that can affect how a respirator fits someone's face, such as the size and the shape of the face, the presence of beards or other facial hair, and then things like scars or certain facial abnormalities that may not allow a respirator to fit in a kind of more standard way, because it needs to fit tightly against the face in order to truly protect the wearer. There are a few different kinds of fit tests. So the first one is a fit check, which is really just a user seal check. And this is done by the wearer at each use, just to make sure that it is properly snug against their face. Qualitative fit tests rely on the wearer sensing any leakage. I'll discuss this more in just a second. And these are done at an initial fit. So when you first get your respirator, you'll do a qualitative fit test, and then they tend to be updated annually. And then quantitative fit tests take actual measurements of leakage or possible leakage. And again, these are done at the initial fit and then updated annually as well. So first we'll talk about fit checks, just these basic checks that the wearer is supposed to do every time they put on their respirator. And you've got little pictures and explanations here of the two different kinds of fit checks that a person can do. You can do a positive pressure fit check, which is where you block the exhalation valve with the palm of your hand, and you breathe out and hold for about 10 seconds. And then you check to see if the face piece is bulging slightly. So if the face piece remains bulging and there are no more leaks between the face and the face piece, then the respirator is properly fitted. But if you detect leaks, then you have to readjust the straps and check again to make sure it's properly fitting. Then you can do a negative pressure fit check, which is where you block, instead of the exhalation valve, you block cartridges with the palms of your hand, and then you inhale and hold for about 10 seconds, and then you can check to see if the face piece is collapsing slightly. So if the face piece remains collapsed and there are no more leaks, then you're good. If you do detect leaks, again, you have to readjust your straps and check again for a proper fit. Qualitative fit tests involve the use of different agents to see if the user can detect the presence of these agents. So in this case, you're not measuring anything, but you are introducing something into the air and asking the wearer if they can detect the agents. So some common things that they use to do these qualitative fit tests is banana oil, saccharine mist. So the banana oil, they'll be able to smell. Saccharine mist, they can taste sweetness through the mist. They can use Bitrex, which is a bitter taste, and they can also use an irritant smoke. These are just common things that they use to do these qualitative fit tests. So they introduce these agents into the atmosphere around the person wearing the mask and ask the person if they can detect them through their masks. Quantitative fit tests involve the actual quantitative measurements of contaminants across the respirators. So this requires using either an artificially generated aerosol or a naturally occurring aerosol to create fine particles in the air. And then they use probes inside and outside the respirator to measure the amount of particles. So they can tell how many particles are on the outside, how many particles are on the inside, which would give them an idea of how many particles were able to cross through or leak into the face area in the respirator. And then you can also do a pressure test where you measure the rate of leakage based on pressure change. So these are ways that a person can and should do their fit tests to ensure that their respirators are properly fitted and actually going to work properly. So if you combine the use of all of these methods, you should be able to properly protect somebody who is in an environment where there are a lot of airborne contaminants that could potentially be hazardous to their health.